We are in Chapter 5, Discrete Probability Distributions. This word discrete here in the title means countable number of values, so keep that in mind as we go through the notes. Section 5.1 are probability distributions. A random variable is a variable. It's typically represented by an x that has a single numerical value determined by chance for each outcome of a procedure. So for example, suppose that you flip a fair coin twice. The outcomes are either going to be heads, 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 tails, tails, heads, or tails, tails. If the random variable x represents the number of heads in the two flips of the coin, then the possible value of x would be either have 0, you would have 1, or you may have 2 possible heads when you flip that coin twice. So notice that there is both an uppercase x and a lowercase x, and that's discussed right below. And so the uppercase x is used to identify the random variable, whereas the lowercase x is used to list all the possible values of the random variable. Next, we have a few vocab words that we need to know. First one is discrete random variable, has either a finite or countable number of values. The values of a discrete random variable can be plotted on a number line with spaces between each points. And we also have a continuous random variable, which has infinite many values. The values of a continuous random variable can be plotted on a line in an uninterrupted fashion. So again, remember, Chapter 5 is discrete probability distributions, and then if you look at Chapter 6, our next chapter, that's going to be continuous probability distributions. So example right below this says determine whether the random variable is discrete or continuous. So the first one that we have says the weight of a steak. Since we're dealing with weight, and weight is something that is measurable, and like we talked about before back in Chapter 1, measurable ideas, it could be so many pounds, then so many ounces, and then you can keep breaking it down even more. So this would be an example of continuous. Part 2 says the number of light bulbs that burn out in the next week in a room with 20 bulbs. So you can literally count how many bulbs are burnt out, and if you can literally count them, this is an example of a discrete random variable. 3 says the amount of rain in Seattle in April. And again, we're dealing with amount of rain, which is a measurement. Since this is a measurement, we are dealing with a continuous random variable. Next, 4 says time required to download a file from the internet. And since we're talking about time again can be broken down from hours to minutes to seconds to nanoseconds, and we can keep breaking this down. This is also an example of something that is continuous. Right below this, we talk about what a probability distribution is. And a probability distribution of a discrete random variable x provides the possible values of the random variable and their corresponding probabilities. A probability distribution can be in the form of a table, a graph, or a mathematical formula. So that first example that we had about flipping a coin twice, there was the different values that we could have for a random variable, which were 0, 1, and 2, and then we'd have to find those probabilities that go along with them. So below this are going to be the probability distribution requirements, and we're going to need this for both Chapter 5 and Chapter 6. So every probability distribution must satisfy the following 3 requirements. So these 3 are definitely ones that we need to know. First thing is there is a numerical, not categorical, random variable x that its numerical values are associated with corresponding probabilities. Number 2 says the sum of all the probabilities is equal to 1, where x assumes all possible values. Number 3 says that the probabilities are going to be between 0 and 1, and yes, you can include 0 and you can include 1 for every individual value of that random variable. The example right below says determine whether the distribution is a discrete probability distribution, and if not, to state why. So again, in order to be a probability distribution, it must satisfy those 3 requirements that are stated right up above. So the first one, part A, we know that x is a numerical random variable. So first thing is x is a numerical. And I'm going to go ahead and put RV for random variable. And if you look at those values for x in the first column, you'll notice that those are numerical, they're not categorical. The next thing that we have to check is to see what the sum of all the probabilities are. And so if you were to add up all of these probabilities, you're going to notice that we get a sum that is not equal to 1. And so since we have a sum of the probabilities that is not equal to 1, we know that this is not a discrete probability distribution. So it's not a discrete probability distribution. So we do not need to check that third requirement, since we know that this is not a discrete probability distribution, since the second requirement was not met. So part B, we have to check this again. And first thing says that x is going to be a numerical random variable. So x is a numerical random variable, and yes, it is, because those are numbers. Next thing that we need to do is add up the sum of our probabilities and see what the sum of that second column is equal to. And this time if you add it up, you'll notice that we have it equal to 1, which is what we need it to be. And the third requirement is going to be that the probabilities, which is in our second column, they all need to be between 0 and 1. And again, it could be 0, it could be 1, they're not in this case. And since we have all three of these are met, we can say that therefore we have a discrete probability distribution. So it is a discrete probability distribution. Right below this we have a probability histogram. And this is going to be horizontal axes are equal to the value of the random variable. And the vertical axis is going to represent the probability of each value of the random variable. The example right below this says hiring managers were asked to identify the biggest mistakes that job applicants make during an interview. Does the table below represent a probability distribution? If so, create a probability histogram. So looking at this, you have your first requirement is that x, your random variable, has to be numerical. And if you look at your values for x, you'll notice that x is not a numerical random variable. So x is not a numerical random variable. And so it is not a discrete probability distribution. Right below this, it says with a probability distribution, we have a description of a population instead of a sample. So the value of the mean and the standard deviation, the variance, are parameters and not statistics. So the mean, mu, for a probability distribution is equal to x times p of x, and then summing those all up, where x is the value of the random variable and p is the probability that correlates with that. The next one that we have is the variance, and we get the variance by taking this and squaring your x's times the probability, summing them all together, minus your mean squared. And that gets us sigma squared, or the variance, where x is the value of the random variable, mu is the mean of the random variable, p of x is the probability of observing the value of that random variable. Then the standard deviation, again, is the square root of the variance. The two that we really need to know are the mean and the standard deviation. But again, to remind you guys, we are using a calculator, so these formulas we don't really need to stress too much about. We can round these certain ways that the book will be doing. For you guys, my open math will tell you how to round, and then likewise on an exam I will tell you how to round too. The expected value is one that we do need to know. Give that a few stars. The expected value, e of x, is the mean value in the long run for many repeated samples of the probability weighted average of all possible values. So if you notice, the expected value is equal to the mean, which was stated up above. So right below this, we have an example that says a lab orders a shipment of 100 test tubes a week, 52 weeks a year, from a supplier for experiments that the lab conducts. Prices for each weekly shipment of test tubes follows the distribution below. How much should the lab expect to budget for the next year's test tubes orders, assuming the distribution does not change? So a few things to be careful with. It does ask for next year, but also notice that they're telling us in weeks. So keep that in mind when we actually go to calculate this. The other thing I would like for you guys to note is that it does say how much should the lab expect. And whenever you see that word expect, that means that you need to think about expected value, E of x. So if you notice, you do have a probability distribution given to you. You have x and you have p of x. So you have a random variable that's numerical. You can add up those probabilities and they will equal to 1. And then also those probabilities are all between 0 and 1, and yes, including 0 and 1. So in order to calculate our expected value, use the formula that was listed up above, which is going to be the sum of x times p of x. And so for this case, we have $10 times 0.40 plus $12.50 times 0.35 plus 15 times 0.25. And when you work this out, we get a value of, and I'm going to go around 2 decimal places since we are dealing with money. And this is going to be, we would expect to spend about $12.13 per week. Now again, it's asking for us to budget for next year. So for the year, we have to take that $12.13 that we would expect to be spending every week and multiply it by 52. And 52 because there's 52 weeks in a year. Multiplying this out, again, money, so 2 decimal places, you get $630.76. So it says how much should the lab expect to budget for next year's test tube orders? We would expect to budget $630.76. Right below this, we have another example. This example says the Mega Millions is a California lottery, and the probability of winning the Mega Millions jackpot is 1 out of 259 million. If you buy one ticket, which costs $1, find the expected value of winning the $104 million jackpot prize. Assume that there's only one winner. So for this, you'll notice that this is similar to what we had previously. It does have the word expect in there. It does ask for the expected value, keeping your eyes open for that. But we do not have a probability distribution. And so we're going to go ahead and create our own probability distribution. And so for this, there's only 2 different events that we have. If there was like a first prize, a second prize, and a third prize, we would definitely have more. But this is just talking about winning, and then obviously the other idea here would be not winning. So you're either going to win or you're not going to win. And so for this, we need to come up with x and p of x for both of these. So I'm going to go ahead and just draw a line here to separate the two. So let's go ahead and first talk about the probability of winning. So the probability of winning, it tells us that it's 1 out of 259 million. So that would be the probability of winning. And then the probability of not winning is the complement of this. And you could do 1 minus that, or from the numerator, there would be 258,999,999 different ways to not win. And then the next thing is that random variable. So what happens if you do not win this lottery? And if you do not win the Mega Millions jackpot, you didn't get any money, but technically you paid to play this game. And so technically you did not win and you lost $1. And we symbolize a loss by putting a negative. I'm going to go to put the dollar sign here, but you lost that $1. How about when you win? When you win, it does tell us that's a $104 million jackpot prize. And so for this, we would have the $104 million, so put your 6 zeros. However, I know it doesn't seem like much in the scope of this problem, but you did still pay that $1 to play this game. So we need to subtract away the $1 that you did spend. So again, to calculate your expected value, it is the sum of x times p of x. And so we have to do this for winning, and we're going to also have to do this for losing. So winning is going to be the 104 million minus 1 times that probability, which is 1 out of 259 million, plus, again, summing these together, the expected part for not winning, which is going to be negative 1 times 258,999,999 all over the 259 million. So plugging this in all on your calculator and calculating an answer. Again, since we're dealing with money, I'm going to go ahead and round 2 decimal places. And you should get a negative answer, and it should be negative 0.60 when you round 2 decimal places. Put your dollar sign on there. So find the expected value of winning this. So what this says is if you were to purchase tickets over and over every week, and you would expect in the long run to lose 60 cents out of every $1 that you've been spending. So usually your odds for this kind of lottery are going to be negative. You will hear them talk about expected value, and when jackpot hits a certain amount, then the expected value you will hear them talk about on the radio or on the news, and saying that this is now when you want to, your chances of winning, your expected value of winning are now positive or have increased to a value that would likely cause you to play this game. So we have another example right below this that says, in a statistical study, individuals are asked to disclose the number of televisions in their household. In the following probability distribution, the random variable x represents the number of TVs in the household. Part A says verify this is a discrete probability distribution. So again, there's 3 things we have to verify. First one is x is a numerical. I'm just going to put RV for random variable. Second thing is we need to take a second and add up all those probabilities in the second column. And when you do, you will notice that we do arrive at 1. And then the third thing is going to be that your probabilities are all between 0 and 1. And looking at those, they are. So yes, all 3 of these are met. So therefore, we just verified that this is a discrete probability distribution. Part B says draw a probability histogram. Remember, histogram is where our bars touch. And for a probability histogram, we are going to have our random variable on the x-axis, and our vertical is going to correspond to the probabilities. So going ahead and drawing our axes on here. Your random variable goes from 0 to 9. And this is your random variable or your number of TVs. And then on our vertical axis, we're going to put our probabilities, which if you look at the probabilities, The largest one that we have is 0.261. So we're going to go ahead and count. I'm going to count by 0.05, 0.10, 0.15, 0.20, 0.25, 0.30. So for the first one, we have a probability of 0.161. So do the best you can. For number 2, for 2 TVs, the probability of this is 0.261. For 3 TVs, we have 0.17. 4 TVs, we have 0.186. 5 TVs, we have 0.11. 6 TVs is 0.055. 7 TVs we have is 0.025. And then the last 2 is 0.010 for 8 and 9. So again, do the best you can since those are very small numbers. Hopefully you can tell by looking at this, your histogram is skewed to the right. So part C says determine and interpret. So underline that word interpret and keep an eye out for that when you are asked questions on an exam or on a project. So determine and interpret the mean of the random variable x. And we can do that by doing our sum of x times p of x. And there's another way to do that rather than doing it by hand. And so we're going to go ahead and use one-var stats like we did previously in previous chapters. But because we have our 2 lists, we have our random variable and our probabilities, or our relative frequencies if you want to think of it that way, we need to use one-var stats, but we are putting it in 2 lists. So you need to put in L1 as our random variable, and our probabilities are going to go in L2. On your graphing calculator, you need to select the button for stat and select enter on edit, and take a moment to enter in all those numbers. So list 1 needs to be the number of TVs, and list 2 will need to be the probabilities that correspond to each of those values. Next, select stat button again, scroll over to calc, and at calc you need to select one-var stats. And if you have the newer style calculator, it's going to ask for the frequency list. And for the frequency list, make sure you put L2 since you did put numbers into that list. And for this one, this is the older style. So hit second 1 for L1, comma, second 2 for L2. This is going to tell the calculator to look at both L1 and L2. When you're done, hit close parentheses. Again, it depends on the style of the calculator that you are using. Make sure you ask if you have any questions. From here, select enter, and you should get a lot of different information. The first one on here that we need for part C is our mean, and then also later on we will need for part D the standard deviation. On the calculator, we arrive at our mean, and I'm going to go ahead and put mu sub x. And our mean is going to be 3.21. Interpreting this, we would say if we surveyed many households, we would expect the mean number of TVs per household to be 3.21. Part D says determine the standard deviation, which you should also have from your calculator. So going back and looking at that, our standard deviation of our random variable is going to be 1.74. Part E says, what is the probability that a randomly selected household has 3 TVs? So going back and finding the probability of having 3 TVs, we just need to look at our table, our probability distribution, and having 3 TVs here is going to be 0.176. Part F says, what is the probability that the randomly selected household has 3 or 4 TVs? So probability of 3 or 4 TVs. And for this, since this is independent, we could just go ahead and add these two together. And so we would add together 3 TVs plus 4 TVs. So we're going to have 0.176 plus 0.186. And working this out, that probability is going to be 0.362. Part G says, what is the probability that the randomly selected household has no TVs? Would you consider this to be an impossible event? So the probability of having 0 TVs, you go back and look, is equal to 0. It does also ask, would you consider this to be an impossible event? And no, we would say no. And the reason why is this is again only from a sample that we had, and this sample we had nobody that had no TVs in their household. However, if we would have gone to another place, maybe like an Amish area, we would have surveyed again, we probably would have had a different outcome of this. So to say it's impossible is pretty strong wording. So right below this, it says, according to the range rule of thumb, the vast majority of values would lie between 2 standard deviations of the mean. So we can consider a value to be significant if it's at least 2 standard deviations away from the mean. And this is again coming from chapter 3, so that's our range rule of thumb. And so again, our mean is in the middle, going out that 2 standard deviations both ways. And so again, a significantly low value would be one that is mu minus 2 sigma or lower, significantly high, mu plus 2 sigma or higher, and not significant values are going to be between those two values of mu plus or minus 2 sigma. So right below this we have another example that says, in the previous example on the number of televisions in a household, determine if 2 TVs is significantly low or significantly high. So in order to figure out significantly low, we need to have mu minus 2 sigma, and significantly high, we have to do mu plus 2 sigma. And there are a few ways to do this problem. This is one of them, and looking at that range rule of thumb. So we do have our mean and our standard deviation from the previous part of the problem. And so again, the mean was 3.21 and our standard deviation was 1.74. I'm going to go ahead and write that in for both of these. And so significantly low values, working that out, we get a value of negative 0.27. And significantly high cutoff would be 6.69. Getting those from our calculator. So what this means here is that a value is significantly low if it's below negative 0.27 TVs, which doesn't make any sense. And then it's also significantly high if above 6.69 TVs. So 2 TVs, which is what this problem was asking about, is between negative 0.27 and 6.69. Since it's in between those two values, we can say that it is not significant. So 2 TVs is not significant. So another way to think about significantly high and significantly low is thinking about it in terms of probability. So significantly high number of successes is X successes among N trials is a significantly high number of successes if the probability of X or more is, and our big thing here is going to be is that it is less than or equal to that 0.05. Significantly low number of successes, X successes among N trials is significantly low number of successes if the probability of X or fewer is less than or equal to 5. So we have an example right below this that says the following data represents the number of speeding tickets individuals received in the past 12 months. First one, part A, says construct a discrete probability distribution for the random variable X. So you'll notice we do not have a probability column over here, so I'm going to go ahead and put P of X. And in order to get our probabilities, we have to take that frequency for each of these and divide by that total number of frequencies that we have, which is going to be 198. This is also called finding your relative frequencies, like we saw in the previous chapters. For probabilities, we're in around 4 decimal places. So I'm going to go ahead and zoom in here. First probability is going to be 0.8535. And again, you get that by taking 169 and dividing by 198. The next one, taking 21 and dividing by 198, we get 0.1061. For the next random variable, we take 4 and divide by 198, and we have that for both of those. This is going to be 0.0202. Part B says to draw a probability histogram for the data. And so for this one, our random variables are only 0, 1, 2, or 3 speeding tickets. So 0, 1, 2, or 3. And this is number of tickets. And then our probabilities do go up quite a different in values. They go from being super small from 0.0202 to 0.8535. So I'm going to go ahead and count by 0.1. So 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and then 1.00. So first one is 0 speeding tickets. The probability of that is 0.8535. For 1, we get 0.1061. And then for 2 and 3 speeding tickets, we're at 0.0202, so very, very small. Do the best you can to show that. And so again, for this probability histogram, we are skewed right. For the next part, it says compute and interpret the mean of the random variable X. So again, we're going to go ahead and put the number of tickets here, which is our random variable, into L1, and then also the probabilities, which is our last column that we just came up with, into L2. On your graphing calculator, find the button for Stat, select Enter on Edit, and take a moment to enter in all those values into L1 and L2. Again, the number of tickets is going to go into L1, and then the corresponding probabilities will go into L2. I'm going to select Second and Quit to get out of this, and select Stat again. Scroll over to Calc, and then select One-Var Stats. Again, the newer style calculators, you need to make sure that you put frequency list as L2. For the older style, select second L1, which would be second 1, comma, second 2 for L2, close parentheses, select Enter, and again, you're going to get a bunch of different information. The first thing that we need is our mean, and then again, later on will also be the standard deviation. From our calculator, we get the mean, random variable of 0.21. And so again, if we were to survey many drivers, the mean number of speeding tickets in the past 12 months would be 0.21. Part D says to compute the standard deviation, which you should also have on your calculator. And going ahead and rounding this 2 decimal places, we get 0.57. And we are never asked to interpret the standard deviation. For part E, it says use the range rule of thumb to determine whether 2 speeding tickets in the past 12 months is a significantly high number of speeding tickets. Significantly high means that we're going to be using mu plus 2 sigma. And we do have the mean, which is 0.21 plus 2 times our standard deviation, which is 0.57. And so working this out on our calculator, we get 1.35. And so it asks for, and again, this is significantly high values. That means that 1.35 or more tickets is significantly high. So the question was, is having 2 speeding tickets in the past 12 months significantly high number? And yes, 2 speeding tickets is significantly high. Likewise for F, it says use the range rule of thumb to determine whether 0 speeding tickets in the past 12 months is significantly low number of speeding tickets. So significantly low means mu minus 2 sigma. And going ahead and evaluating this, plugging those values in that we had calculated for our mean and our standard deviation. When we do, we get negative 0.93. And so for it to be significantly low, it's going to be negative 0.93 or less is significantly low. And I know that doesn't make sense, but the question that we're asking about is 0 speeding tickets. So we'll say no, it's not negative 0.93 or smaller. So no, 0 speeding tickets is not significantly low.